Hi, I'm Sanjay Patel. In this video, we are going to prove another useful test for convergence of infinite series. It is known as the Cauchy's root test. So let us write down the statement of this theorem. Let sigma an be a series of positive terms. Okay. And suppose limit n tends to infinity of an raised to 1 upon n is equal to L exists. So we assume that this limit exists. Okay. Then prove that say number 1, if L is less than 1, then sigma n is convergent. L is less than 1, then sigma n is convergent. If L is greater than 1, then the series sigma n is divergent. And the third thing is, for L equal to 1, if the value of the limit is 1, then the test fails. We cannot determine whether the series is convergent or divergent. So these are the conditions which are exactly similar to the practical ratio test due to the real limits. Okay, so let us prove this. Proof also goes on the similar line as we have proved the D'Alembert's ratio test in the limit form. So the first part, suppose the limit L is less than 1 here. So first we'll prove this case. Okay, for the value of the limit L less than 1, the sigma n is convergent series. Okay. Now here all the terms a1, a2, a3, an of this series are positive. So therefore the limit L is also non-negative. So since an is greater than 0 for every n, okay, so that implies limit n tends to infinity an raised to 1 upon n, okay, that is also non-negative. That is, L is non-negative. So L is a non-negative number between 0 and 1, and we want to begin the proof by taking a number r between L and 1. So suppose this is our number line and we have two numbers here, one is 0, another is 1. The number L is between 0 and 1, so suppose it is somewhere here. Okay, now we choose another number, say small r, such that L is less than r and r is between 0 and 1. So we choose another number r between L and 1 in fact. So let us write that thing. Choose 0 less than r less than 1 such that L is less than r. Remember that there are infinitely many real numbers between L and 1. I can choose any number as r between 0 and 1 which is greater than L, or L is less than r. Okay, so keep in mind that L is less than r. Now consider the fact that the limit n tends to infinity an raised to 1 upon n is equal to L. Okay, and now for this we are going to apply the definition of limit of a sequence. So again, let us quickly recall what is the definition of limit of a sequence. We say that limit n tends to infinity xn is equal to x if and only if for every epsilon greater than 0 there exists some positive integer m belongs to n such that whenever n is greater than or equal to m implies we have xn minus x is less than epsilon. This is our definition of limit of a sequence, and that we want to apply for this limit of the sequence a n raised to 1 upon n. So here our xn is xn is a n raised to 1 upon n. Xn is a n raised to 1 upon n, and x is the limit L. And now L is less than R, so R minus L is greater than 0, and that positive number I want to take as epsilon. So I will take epsilon is equal to R minus L. So let us begin by that. As we have L is less than R, implies R minus L is greater than 0. So taking epsilon is equal to R minus L greater than 0, there exists some positive integer. By definition of limit of sequence, there exists some positive integer n such that for every n greater than or equal to m implies mod of xn minus x, that is mod of a n raised to 1 upon n minus L is less than epsilon. Okay, and this we want to write in the simple form by removing this modulus. So this I can rewrite as, this implies L minus epsilon less than a n raised to 1 upon n is less than L plus epsilon. So what we have proved is this: for every n greater than or equal to m, this thing is true. Okay, here this a less than b less than c is true. Okay, so I want to use only this inequality, that b is less than c. Everything is true. A is less than b as well as b is less than c. So I can write this as therefore for every n greater than or equal to m implies a n raised to 1 upon n is less than L plus epsilon. But what is L plus epsilon? L plus epsilon, from this you can say that L plus epsilon is equal to R. So I can write this implies a n raised to 1 upon n is less than R, because epsilon is equal to R minus L, and that gives us L plus epsilon is equal to R. Okay. Now taking nth power on both the sides, here we'll get a n less than R raised to n. Okay. And what we have proved here is this thing. Therefore, for every n greater than or equal to m implies a n is less than R raised to n is proved. Okay. Now we have two series here. One is sigma a n, and other, the right hand side sequence gives you the geometric series sigma R raised to n. Okay. So I can use the comparison test here, because you know what is comparison test. If we have a n is less than or equal to k into b n for every n greater than or equal to m for some positive real number k and some positive integer m, and if sigma bn is convergent, then sigma an is also convergent. Okay, so I want to use this comparison test. Here k is equal to 1 in our case, this is 1, and this bn is the series R raised to n. Okay, and an is as it is. So k is equal to 1 here. So using this this comparison test, let us write here as result number 1, and then we can mention that here the series sigma R raised to n, this series for n is equal to 1 to infinity is convergent because it is a geometric series. And the ratio of this geometric series is between 0 and 1, and we have 0 less than R less than 1. So the ratio is between 0 and 1. That is very, very important. Otherwise, the series is not convergent. So sigma R raised to n is convergent. And therefore, by comparison test, we can say that sigma an, this series from n equal to 1 to infinity, is also convergent. Okay. The first part is proved. If the limit L is less than 1, then the series sigma an is convergent. Now consider the second case where L is greater than 1. So case 2, suppose L is greater than 1. Okay. What is L? L is the limit of the nth root of the sequence an. Now as L is greater than 1, L minus 1 is greater than 0. Now limit n tends to infinity, an raised to 1 upon n is equal to L. This is given to us. Okay. So we'll apply the definition of limit of a sequence by taking epsilon is equal to say L minus 1 because it is a positive number. The definition holds for any given epsilon. So for epsilon is equal to say L minus 1 greater than 0, we can always find some positive integer m belongs to n such that for all n greater than or equal to m implies mod of an raised to 1 upon n minus L, mod of xn minus x is less than epsilon. Okay. So that gives us L minus epsilon. If we remove this modulus, we can rewrite this as L minus epsilon raised to, L minus epsilon less than an raised to 1 upon n less than L plus epsilon. Okay. Now in this, I want to consider only this first inequality. A less than B and B less than C. Everything is true. So I can write it as, for every n greater than or equal to m implies an raised to 1 upon n is greater than L minus epsilon. But L minus epsilon is equal to 1 because of our definition of epsilon. So I can add this is greater than 1 because epsilon is L minus 1. So L minus epsilon is 1. And that implies taking nth power both the sides, an raised to 1 upon n raised to n, that is an, is greater than 1 raised to n, and that is 1. So what we have done here is taking nth power on both the sides of this inequality. Okay. So what is proved? For every n greater than or equal to m, an is greater than 1. So therefore, the conclusion from this we can make is, therefore limit n tends to infinity of an is always say greater than or equal to 1, and therefore limit n tends to infinity an, that cannot be 0. Okay, that cannot be 0 because all terms are strictly greater than 1. So limit of an as n tends to infinity is greater than or equal to 1. That means the limit cannot be 0. And if the limit of the nth term of a series sigma n is not 0, then we can say that the series is always divergent. So this implies the series sigma n is divergent series, is divergent for n is equal to 1 to infinity. Okay. So for L greater than 1, we have proved that the series sigma an is divergent. And now the last case, which is in the given statement, for L equal to 1, the test fails. You want to show that this test fails for L is equal to 1. Means just finding the limit L, you cannot determine the convergence. So in this case, we should provide an example in which the limit of an raised to 1 upon n is 1, but the series may be convergent or divergent. So I will consider two different series, and both the series, the limit L will be 1, but one is convergent and other is divergent. So consider the case 3. Suppose L is equal to 1. Okay, in this case, we must provide two series for which, as I told you, limit of the nth root of an is 1. So consider two examples. First of all, let us take example number 1. Consider the series, say sigma n is equal to 1 to infinity as sigma 1 upon n square, n is equal to 1 to infinity. Okay, this is a p series, it is clear, and p is equal to 2, which is greater than 1, therefore this series is convergent. Okay, so as p is equal to 2, which is greater than 1, implies this sigma an is convergent series, is convergent because it is p series. So by p series test, we can see this, and let us call this as 1. Okay, no need to write 1 here. Fine. The next step I want to consider here is limit of an raised to 1 upon n, that is limit of the nth root of an, that is limit n tends to infinity of 1 upon n square raised to 1 upon n. This we can write as limit n tends to infinity 1 upon n raised to 1 upon n whole square. This also we can write. And we know that as n tends to infinity, nth root of n tends to 1. So this is equal to 1 upon 1 square is equal to 1. So the reason is limit as n tends to infinity, nth root of n, that is n raised to 1 upon n is 1. So we are using this formula for writing the limit of n raised to 1 upon n, and that is 1. So what we have proved here is, thus in this case, therefore limit n tends to infinity an raised to 1 upon n is equal to 1, that is L. So L is equal to 1 and the series is convergent. Thus L is equal to 1 and the series sigma n is convergent. So this is first case or first example. Let us consider another example. So number 2, consider another series sigma n equal to 1 to infinity as sigma 1 upon, say simply n is equal to 1 to infinity. And again it is clear that since this is p series where p is equal to 1, so as p is equal to 1, which is less than or equal to 1, implies this series sigma n is divergent series. This is divergent series by the p series test. Okay, by the p series test. What we want to now find is limit of the nth root of an. So limit of the nth root of n, now limit n tends to infinity, an raised to 1 upon n is equal to limit n tends to infinity an, that is 1 upon n raised to 1 upon n, and that is equal to limit n tends to infinity of 1 upon n raised to 1 upon n, and that is nothing but 1, because as n tends to infinity, nth root of n tends to 1. Again we are using the same formula, a limit n tends to infinity of nth root of n is equal to 1. So again what we have proved is limit n tends to infinity, nth root of an tends to 1. So this is our L. So in this case also we are getting the limit 1, but the series sigma an is divergent. So let us write down that conclusion. So thus L is equal to 1 and the series sigma an is equal to 1 to infinity is divergent. So from these two examples it follows that, okay, so from these two examples, from 1 and 2, it follows that for L is equal to 1, the test fails because we cannot determine the series is convergent or divergent. So we have proved all the cases that if you find limit as n tends to infinity of a n raised to 1 upon n, and if it is L, this is limit n times infinity a raised to 1 upon n is equal to L. If L is less than 1, then given series is convergent. If L is greater than 1, the series is divergent, but we cannot say anything for L is equal to 1. So whenever you want to apply the Cauchy's root test, this is called Cauchy's root test, then take the nth root of an and find the limit of that nth root of an. So this theorem is known as Cauchy's root test because we are taking the nth root here. Okay, so this theorem is proved. Now in the next lecture, we are going to discuss problems based on the ratio test and the root test, that how to determine convergence of given series of positive terms using these two results. So thank you.